depth first search, and we went through this example. I'm going to go through it again very quickly this time so that we can discuss some of the important ideas related to DFS. So we said that in DFS we pick a source, and in last time we picked this as the first source, and we said that this is going to be, well, initially everything is white, then this is gray, and we said that this is event 1. Then we checked the neighbors, we went to B, and then checking the neighbors of B, we have C and E. We went to C just following the alphabetical order. So now this is gray, this is 2, and then we went to W, and now this is gray, and this is event number 3, and the only neighbor of C is D. So now this is gray, and this is 4. Then when we got to D, we have to go back, right? So why do we have to go back? Because the only neighbor of D is B. Now last time we said that if we have an edge from the current node to a previously visited node that is gray, then this is a back edge. Why is that? So who can make a clear argument why whenever we have an edge from the current node to a node that is gray, that's a back edge, or that indicates a cycle in the graph? Why is that? Well, because what does gray mean?
We've already visited it.
Well, gray means two things. It means that we have already discovered it, but it also means that we haven't finished it. Yeah. So remember these 3 states: discovered, undiscovered, discovered but not finished, and finished. And we colored this with white, this is with gray, this is with black. Now the point is, discovered but not finished means that we have discovered this node, but we are still exploring the nodes that are reachable from this node. So the fact that B is gray means that B has been discovered, but we haven't yet completed exploring the nodes that are reachable from B. We're still exploring the nodes that are reachable from B. Well, what does this imply? It implies that D is reachable from B, right? So because we're still exploring the nodes that are reachable from B. Now, D is reachable from B, and we have just discovered an edge that will take us back to B, which means that this edge will necessarily complete a cycle, right? So the fact that this is gray implies that there is a path from B to D. And this edge indicates that this edge will take us back to B, which means that this is a back edge. Now, last time I emphasized that the back edge is not an absolute property of an edge. So you cannot say that this edge is absolutely a back edge, because it depends on your traversal and on your source. So if we had selected D as our first source instead of A, then this edge would have been a forward edge, not a backward edge. Right? So we would have started our depth first search by going to B, then possibly then going to C, then to D, and in this case, which edge will be a back edge? So if we did if D was the source, then we went to B, then to C, then to D. In this case, which edge will be a back edge?
CD.
Yeah, CD will be a back edge in that case. Okay. So now we get to this edge. So this is a back edge. So we backtrack now. So this is black, and this is event number 5. Then we go back to this. Now, when we go back to this, remember, we are implying that we are using what data structure to guide the search? Stack. Because you know, when you start from A, you push A on the stack, you push B on the stack, you push C on the stack, then you push D on the stack. Now you want to go back. You hit a node that has no neighbors to explore, because all of its neighbors, well, the only neighbor that it has been explored already. So we want to go back, and when we go back, we just pop D off the stack. When we pop D off the stack, we get C. Now, as we will see when we write the code in a minute for DFS, we're not going to use the stack explicitly. We're going to use the stack implicitly by using recursion. Because when we use recursion, you are implicitly using the stack because you are using the system stack. In this case, you are implicitly using the system stack that manages function calls. OK. So now we go back to this. This is going to be 6, and we finish this. And then we go to B. Now, should we finish B? Should we finish it?
No.
No, we shouldn't, because we haven't explored this yet. So we have to explore this, and this becomes gray. Then we discover that all the neighbors have been visited. So we make this black, and this is going to be 7 and 8. Then we go back to B. Now we have completed this. So now this is finished black, and this is 9. Sorry, I don't. So this is going to be 2 and 9. Then I go back to A, and now have we completed exploring the neighbors of A? Now I will first have to check this, but then I will discover that this is already black, so nothing to explore. So I will finish this and say that this is number 10. Then I find another source, and this could be H. So I say this is gray, and this is 11, and I may explore this neighbor. But then all the neighbors have been explored already. They are all black, black, and black. So I just backtrack. But now this is going to first become gray, then black. Then this is going to be 12 and 13. Then I go back to H. But I'm not done with it yet because there is still another neighbor. And so I go to this neighbor, and this is gray. So this is event 14. Then all the neighbors have been discovered. So this edge leads to a black. This edge leads to a gray, which means that this is a back edge. And this is clearly a back edge. Now there is clearly a circle here, or a cycle. OK, and this is, I finish this at 15, and then I go back, and this is 16. OK. So now we did this last time, but we haven't drawn the DFS tree. So the edges that I marked with red are the DFS edges, the edges that we have used in the DFS. Not the back edges, not the edges to black vertices, but the edges that represent our exploration. So these red edges that we have traversed. So in this case, these edges are going to draw a tree. A, then B, then C and E, or B, C, D, and E is a child of B. So this is one tree. And the other tree that starts with H, oh, I forgot to mark this as a forward edge. The other tree, which starts with H, is going to have two children, F and G. So this is tree 2. So basically, each source vertex is going to give us an edge, a tree. So in general, DFS is going to give us a forest. Forest, which is a set of trees. Set of trees.
Is there any reason why we're keeping track of the numbers?
Oh, the numbers? Well, they have their own uses. So we will probably see some examples in which we can use these numbers. But these numbers indicate certain orders. So if you look at these numbers, this is the discovery time of the vertex, and this is the finish time. We will show some examples in which we use these numbers, but we are tracking them here for completeness and to indicate the order in which we do things. So to indicate that we first discover A before discovering any of these vertices, but A in fact will be the last vertex to be finished in this part of the graph. Yeah. So they can be useful, yes. But here too, we're showing the numbers to explain, in detail how DFS works. Okay. Any other questions? Yeah.
So how would it be different if it was undirected?
Oh, undirected? Well, if it's undirected, then you can think of an undirected edge as a two-way edge. So it's like, an undirected edge is equivalent to, so an undirected edge between A and B, this is equivalent to an edge from A to B and an edge from B to A.
Here we doesn't get a forest.
I'm sorry?
Here we doesn't end up in a forest in undirected graph.
We never end in a forest?
I'm asking that do we end up in a forest getting two DFS trees?
Well, that's an interesting, that's an interesting point. So you are saying that in every undirected graph, we will never end up with a forest. So you're saying we end up with a single tree. Okay. And okay. So this is true under one condition. So, under what condition will this be true? Yeah.
There's no unconnected nodes.
Yeah, exactly. So if it's undirected, if the graph is undirected and is connected, then yes, you will end up with one tree. No matter which vertex you pick as a source vertex, you will end up with a single tree. But if the graph is disconnected, then you may end up with you will end up with multiple trees. So for example, if your graph is any undirected graph, yeah, so this, by doing this, no matter which node you pick as the source, you will visit all of them because you can go to any one of them. But if your graph had another piece or another subgraph that is disconnected like this, so if your graph consists of two pieces or two disconnected subgraphs, this is subgraph 1, this is subgraph 2, and they are disconnected, then you will end up with two trees. So in fact, DFS in this case will be a good way of counting how many disconnected subgraphs you have in the graph. If your graph is one piece or two pieces or three pieces. Okay, so that was a good point. Okay, but even if the graph is directed, even in this case, we could have ended up with one tree if we had chosen which vertex? H or G. Yeah, if we had chosen H or G, we would have ended with one tree. So this is, okay, let's draw it here. If H was selected as the source, then we will end up with H, then it will have F and G, and below F, in fact, F is going to connect to A, and then A will have this whole tree below it. So we will have A, then B, then C, then E, then D. Okay? So if we had chosen H, we would have ended with a single tree, a forest that consists of a single tree. So you can think of the DFS as a way of extracting a tree out of a graph, or selecting a subset of the edges in the graph. So you're basically selecting a subset of the edges in the graph. Now, generally speaking, what's the mathematical relation between the number of edges and the number of vertices in any tree? So in any tree, the number of edges equals, what's the relation between the number of edges and the number of vertices? Just look at these examples. What's the relation? So this has 3 vertices and 2 edges. This has 1, 2, 3, 4, 5 vertices and 4 edges. And this has, well, we know that the same relation will hold. What's the relation?
-1.
Yeah, so E is V minus 1. So can you give me an argument that proves basically that in every tree the number of edges is equal to the number of vertices minus 1? That this is true for any tree. In any tree the number of edges is equal to the number of vertices minus 1. Can you give me a simple argument that shows this?
By definition, edge is a connecting point between 2 vertices.
Okay.
So ideally, if there are n edges, then it should be connected to n plus 1 vertices.
Where does the V minus 1 come from? Yeah.
So in this algorithm, every time you have a node, you go 1 over, but then when you find a back edge, you don't count that one. So you're gonna.
No, forget about this. Just look at the trees. Why is it true that in any tree, the number of edges is the number of vertices minus 1?
Because the last one and the first one won't get connected. Like is won't get.
Okay, not clear. Well, in a tree, each vertex has a unique parent, right? So for each vertex, there is a unique parent. But there is one vertex in the tree that doesn't have a parent. So for any vertex in the tree, there is a parent. And the fact that there is a parent means that there is an edge leading to this vertex. So it's its parent, and this is the parent of this vertex. So there is one vertex in the tree that doesn't have a parent, which is the root of the tree. So if this is the root of the tree, this doesn't have a parent. All other vertices have parents. So there is one parent per vertex. Okay. So that's why we have the number of edges is the number of vertices minus 1. Okay. So now in a graph, a graph in general can have more than V minus 1, can have more than V minus 1 edges, because it can have up to V times V minus 1 or V times V minus 1 divided by 2, depending on whether it's directed or undirected. So the DFS will basically extract a tree out of a graph. So you can think of it as an algorithm that selects a subset of the edges that form a tree, or that form multiple trees, in this case, a forest. Or each search forms a tree. Each source, a search that for each source we form a tree. Okay. Now, okay, so this is the DFS. and these are the trees and the forests. So now, any questions on what we have covered so far? So let's now write the code for DFS. Okay. So there will be two functions, the main function and the function that will recursively explore a vertex. So the high-level function will do the following. DFS of graph, we're given a graph without a source. So first of all, we'll go through for each vertex u in G, we set u dot, we set, in this case, we are going to set the discovery time and the finish time. So u dot d is the discovery time, and u dot f is the finish time. And the color also, u dot color is the color. So we will set u dot color initially to white, and u dot pi to null. Now what's pi? What do we put in pi? The?
Parent.
Yeah, the parent, like we did in DFS. So pi is, u dot pi is the parent. Then we set the time to 0. Then we just go through the vertices and try to find a source for each vertex u in G. Now, which vertices qualify for sources? What's the condition that a vertex has to satisfy in order to qualify for a source? Can we just pick any vertex? So initially, yes. Initially, we can pick any vertex. Any vertex is good for a source. But after we do the first exploration from the first source, we cannot pick any vertex as a source. So that vertex must be what? White, yeah. It must be white, exactly. Because it must be a vertex that we haven't visited. So only white vertices qualify for sources. Initially, all vertices are white, so they will all qualify. But after we do the first exploration, some of the vertices may not qualify. So if u dot color equals white, then explore the graph from u. And what is explore? Now, explore is the recursive function that will explore the graph from one source. So explore G and S. So when we explored A, what did we do? The first thing that we did, we set the color to gray. So we did s.color equals gray. Then we incremented the time and set it to the discovery time. So then we did time plus plus, and we said s.time, s.discovery time equals time.
So time is a global?
Yes, you can think of it as a global. Yes, you are right. Then, we set these. Then we find a neighbor. So we have to go through the list of neighbors, the adjacency list. Going through the adjacency list is something that we will be doing in all the algorithms that we will be studying. So we'll have to go through the adjacency list for each neighbor V that belongs to the adjacency list of U. or u.adjacency list, let's call it u.adjacency list, any v that belongs to the adjacency list of u, we just start exploring that. So we do the same thing. We repeat the same thing. We recursively explore that neighbor. So we just do explore G and V. Now, under what condition will we explore? Under what condition will we explore a neighbor?
V is white.
Only if it is in white.
If it's white, yeah. So if it's gray, that will tell us that there is a cycle. So we can put this here. If v dot color equals gray, then print cyclic graph. Print that the graph is cyclic. If v dot color equals white, then explore v. So if it's white, explore. If it's if it's a back edge, all what you do is just you detect cycles and then you print a message or whatever, or you mark that graph as cyclic, or depending on the application. Then you explore. Then where do you set the color to black? Where do you set the color of S to black?
We visited all the neighbors of them.
Yeah, exactly. After we visit all the neighbors. So after this whole loop completes, this loop is going to recursively visit all the neighbors. After we recursively visit all the neighbors, like we did with A, we did not set it to black until we have recursively visited all the neighbors. So at that point, we will do S dot color equals black and time plus plus and S dot finish equals time. Okay, so we forgot to set the parent. So where do we set the parent relation?
In the for loop?
Yeah, in the for loop. So here we can say if, okay, so where should we put the setting of the parent? So should we put it here? Or inside the if? Yeah, inside the if. Only if we are exploring, then only then will V be a child of U, or U be a parent of V. So here we should put V dot pi equals U. And we can put it before or after the explore. That doesn't matter because pi is not used inside the explore. Okay.
Wait, V dot pi equals S.
Oh, sorry. Yeah, you're right. Yeah, S. Yeah, we call it S here. Yeah, it's called S, not U. Okay. Any questions on DFS? Well, now the next step is analyzing the algorithm, and the analysis is going to be very similar to BFS. Very similar. So this is a loop that visits all vertices. So this is theta of V. And this, how many times will this loop get executed? So in fact, how many times will the if statement get executed? V, exactly V. So this is theta of V. But how many times will the explore get executed?
if there is one white vertex.
Oh, the aggregate.
What's that? How many times will the explore get executed? How many times will we explore?
Explore every vertex, right?
No. How many times will we execute this line? So in this example here, how many times will explore get executed? In this example. So, twice. Why twice?
First time when we are starting with A.
Yeah, exactly. Yeah. So first time we started with A, and when we explored A, it explored all of these except H, G, and F. Then, when explore returned, all of these vertices were colored black. So black, black, black. All of these were colored black, but H, F, and G were colored white. Then, the second time around, we discovered, we found a vertex that is white. So we did a second exploration. And in the second exploration, we colored the rest of the vertices. We discovered and colored the rest of the vertices with black. So the number of times this is executed is equal to the number of trees in the forest. And it's equal to the number of sources. Okay? Any questions on this? Yeah, so in this case, if we had, in this example, if H was the first source, then explore will be executed only once. Because of course, I'm referring to the execution of explore here on this line. How many times it will get executed on this line. But then it will call itself recursively, right? Okay, so this is going to be of V. But now inside, so this is constant. These are constant time operations. We have a loop here. And the number of executions of this loop is going to be the same as BFS. So the line in blue here, whether you think of this line or this line, this is going to get executed exactly E times. Exactly E times if the graph is directed or undirected. So E times if the graph is directed, and if it's undirected, 2E. Exactly. So E times if directed, and 2E if undirected. Because if it's undirected, then each edge is equivalent to 2 edges. Each undirected edge is equivalent to 2 directed edges. But in both cases, E or 2E, this is theta of E. So in fact, this is theta here, because eventually you will visit all edges in DFS. So this is theta of E. So now what's the overall running time? What's the overall running time? Yeah, it's going to be V plus E. Exactly. So remember that this is theta of E in aggregate. In aggregate, meaning throughout the entire algorithm, this line will get executed E or 2E times. So the overall running time is going to be theta of V plus E for DFS. Okay. Any questions? Is there any?